Okay, so I will read for you the introduction of the most fundamental paper in nonlinear dynamics, the paper that we are covering in last lecture and this lecture. So here it starts. It's a paper by Stephen Smale called Differentiable Dynamical Systems, which is kind of dynamical systems we care about in physical applications. And here is the first paragraph, first line says, Introduction to Conjugacy Problems for Diffeomorphisms. This is a survey article on the area of global analysis defined by differentiable dynamical systems, or equivalently the action, differentiable, of a Lie group G on a manifold M. Here, diff M is the group of all diffeomorphism of M, and the diffeomorphism in differentiable map is a differentiable inverse. Daga, daga, daga. Our problem is to study the global structure, i.e. all orbits of M. Now, suppose you're experimentalist across the whole and you have a dynamical system like a lizard on the sand. Are you going to know that this paper is the paper that has the truth in it? Because this is the fundamental paper. This is where the Smale horseshoes were introduced, and this is what I'll explain today. So there's a great, dynamics is extremely rich because people in every profession, from economics, psychology to topology and mathematics, algebraic geometry, the broad range of things, and it's extremely hard to understand each other. So if you don't understand me, join the club. It's you're in the general world of nobody understanding anybody. So what I did last time, which I didn't have pleasure of your company, but it's on the video, so it's on the web, you can watch it. The ice fall is continued. I discussed the stretching and folding in dynamics. So the idea was the dynamical systems that seem to exhibit chaos. It's usually very hard to prove that what you're looking at is actually mathematically, rigorously chaotic dynamics, meaning that all orbits are hyperbolic and unstable, and there's exponentially many of them as a function of time. I use this very simple example cooked up by a chemist called Rossler. Now, I don't know if I should mention it. Rossler didn't make himself, he's embroiled in legal battles with his University of Tübingen, but he didn't make himself endeared to physicists because he was one of the proponents that when the high energy hadron collider turns on, it'll create a black hole, and black hole will eat our planet. So, but he's a classically educated man, very impressive. And he wrote some equation trying to understand Lorentz dynamics, which said that if you take an interval on the attracting set of those equations, that interval gets stretched, and then as it goes in its merry way, it starts getting folded, it starts getting squashed, and it comes back in something that seems to be a line, but it's actually several Fermis thick if the original interval was a centimeter long. So that's Rossler flow, and it's very easy to simulate. And the main beautiful thing about it is that first, if one does Poincaré section, and at the moment I'm in a state of shock because I've just been informed by reliable sources that nobody understands why I'm teaching you Poincaré sections. So there we are. Poincaré section is something that looks pretty boring. in this case, if you take this Poincare section. But it's three-dimensional for Poincare section, it's two-dimensional plane, and the flow seems to live on the line, so we look at the return map. And one finds out that this return map, which is the map if you measure the distance, curvilinear distance here, from the fixed point and along its unstable manifold until it folds back into itself. This is this point. It turns out that that's a very pretty map, which you can understand in great detail. Looks something like that. And it turns out that when you think about it, if you understand solutions dynamics on this map, you understand it in full state space. Because any point here in this map, it's actually embedded in a two-dimensional plane, which is embedded in three dimensions. So you have full information. So this is not one-dimensional map in the sense that every point here, you can go back all the way here and discover that that point is right here. So if I am at point X of S, if I am here, point X of S, then I actually have all coordinates of this thing. Now the reason why this is sweet is that it turns out that when we look at fluttering flame front or we look at Navier-Stokes equations, the same kind of thing happens. This is 1 million coordinates or 64 or 10,000. But if we find a nice Poincare section which is small in some sense, this is extreme case, it looks like a line, then we can study dynamics there and we can go back and forth the full space and we can predict existence of trajectories. It's very easy to understand here, and they're very hard to understand in the original problem, because in the original problem they do something. Here it's not very complicated because there isn't much they can do, but they go around and they do something before they come back. For example, if there are periodic points. So if you can find them here, we can go back and we can go back and we can go forth. And it costs you nothing but thinking, because this is all easy to compute. It's not a horrible thing. Now, so for some reason, I worked in nonlinear dynamics for a long time. Nobody understands me, nobody reads the paper. Okay, fine. But there was one paper, I have a colleague called Itamar Prokacha, and we made an agreement. I can't stand the way he writes it because it's not precise enough for me. So I did something, he wrote the paper, I never saw it. I'm totally outraged by this paper. It's really badly written. And it's the most cited dynamics paper that I have, because it's about recurrence plots. So we do it all the time on third and fifth floor, and it's a really stupid idea. I had much better theory already then, but my colleagues didn't understand it. And this is the most cited thing. So the dummy thing is to say, well, I just run around and when I come back closer on, that's a good guess for finding a periodic solution, so I'll start it. And of course, if you do it in one dimension, anything will work, no matter how stupid the idea is. But if you do, the real problems, like a swimmer swimming to Havana or something, with many degrees of freedom, she will not be held by this. She has to really rethink it. And the theory, which already existed then, says don't do that, but you look at equilibria, look at the unstable manifolds, you look at how they fold, you use topology to find the solutions, and you fill out the puzzle systematically, hierarchically. Just don't run the computer without thinking. That nobody reads, but this easy idea that you just run computer and produce a number, that seems to be going pretty well. So this is the motivation. Now, this course could be taught differently. So in mathematics, one starts with this, and eventually one says it has something to do with flows. It's not in my taste, but I might be wrong. Maybe it's pedagogically wrong to have first Cauchy flows and then maps, because maps are much simpler. Now, the reason why maps are much simpler is because this particular map written here, so unimodal map of the interval, so this is unimodal map. And the other map that we looked at recently, which look like that, but I'll make it smooth rather than having, this is an example of bimodal map. So unimodal maps have a very crisp notion of topological partition. You look at it, there is a point which is called critical point, xc, in which the map has zero slope, and it's monotonically increasing on one side and monotonically decreasing on the other one. And topologically means that this side is a stretch side, and this side is stretch, and because this is, it comes back and gets folded and comes back oriented in a different way. This is stretch and fold. So this is a very robust topological notion. Either your neighbors, go away from you, or your neighbors go away from you and get flipped around. So if you look at bimodal maps, so the theory I explained for unimodal will work for n-modal maps. It'll be the same story. There'll be a left interval. Everybody stretches and flips, looks like that. There is a central interval wherever it stretches. And then there is a right interval where everybody flips. So that's very topological notion. And it turns out this is extremely powerful because this will enable us to enumerate all possible solutions before we actually compute a single one of them. So we will know exactly what we are looking for. It will not be fishing in the dark. Did I ever tell you about the fishing channel? I must have told you this. I was Mitchell Feigenbaum, who is a very good physicist, and myself were being recruited to start a center of nonlinear blah in what we call Black Hole, Virginia. And as a part of recruitment, very important professor took me to his home. First he took me to the golf course. Now, one thing I don't care about is golf, right? But if I came there, I could play golf at his golf course. Then he took me to his home, and in the home there was like a fish tank, which is the entertainment area with a huge television screen. Now this is 20 years ago, so huge television screen was lots of money. And we sat down, and he was watching the fishing channel. So it turns out there is a fishing channel which is 24 hours a day fishing. And a particular program is called night fishing. So night fishing works like this. You look at the black screen, and there's some kind of noise. And every so often some grinning fisherman with rubber boots up to here shows up in a light holding a fish and grinning. And then he vanishes. So this is the recurrence plot methodology of finding solutions. You're in the darkness, every so often you catch something, you come here, and we have no idea whether you caught all the fish, whether the fish you caught is the fish you want to eat, whether it's an important fish, etc. We have no idea what this thing is, but a computer brings it back. But for unimodal maps, we can do much better. And the main idea is topological. There is a diffeomorphism. It turns out it's not smooth, but it won't matter. Here it's saying that for a map like this, there is another map which is really easy to understand. So there's a 10th map, which has one branch goes up, one branch goes down, but this is simple. Its slope is 2, and this map just multiplies by a factor of 2. So it's really easy to understand. But the really important thing is that I can associate with the critical point, I can associate an interval. saying that map actually cannot reach all the way to the length of unit interval. You know, it doesn't stretch far enough. It can reach only that far. So that's a dike map. That's, again, the Dutch theme of today. The Dutch are good in speed skating and making dikes. And that's a very simple map. And topologically, these guys are the same. So you can write some conjugacy, which turns out maybe not so easy to do in practice, but there's a topological conjugacy. So if you understand what happens with this map, you will understand what happens with all maps of this type, no matter whether they look like this, or they might look like that, they might look like that. In applications, you'll find very weird maps. As long as they're monotone, you're fine. They're all in the same class. Yes?
Is the vertical axis on the tent map to the right? Yes. Is that an open interval or a semi-open interval? Or
We define it to be contained within 0 and 1.
fully?
So there,
I'm interested in the cusp point. That was all I was thinking about.
this cusp, I think you,
That's why I'm asking if it's open.
yeah, I think you want to call it an open interval because this cusp is a very special
Yes.
feature. So, good question. So let me, so if the cusp is extremely important for the smooth maps, and if the cusp touches the unit interval, then its future is very special. This point, critical point, maps to the fixed point. So this critical point is called pre-periodic. And the special case that it is prefixed point, which is a special point, case of periodic points. And in that case, you really have to deal with this differently than its infinitesimal neighborhood. And it's very important to understand the topology. And in the book, there is a conjugacy. So as a problem set, ULA map, every point on this map can be mapped into the tent map. So that's called ULA map. So this is parabola. So this was designed, this map was designed, this was the first, physics application or mathematics application of know-how that went into creating hydrogen bomb, because Ulam was the father of hydrogen bomb, a mathematician at Los Alamos. And once they decided war is over, let's go to fundamental problems. So Ulam, Fermi and Pasta is another physicist who worked at Los Alamos. They decided to go and numerically investigate equipartition theorems of statistical mechanics, which by that time could not be tested. They were the first people to have computers to be able to test it. So they decided designed something called Ulam Fermi Pasta model, which is extremely important and went to invention of solitons and lots of other things, because the first time they tested the ideas, it turned out it didn't work. Things don't equipartition. So this is an extremely important step in development of nonlinear science and also statistical mechanics, far from equilibrium. And he needed a random number generator to do statistical mechanics, so he decided to use a parabola as a random number generator, because if you start with some number here, it'll produce a random sequence statistically. It looked to him. It's not quite random, but it's pseudo-random. So this is one possible method of generating the sequences. And this, if this is a parabola, Then there is explicit map in terms of signs, a trigonometric mapping that maps parabola into this line, with exception of this point. So it's very crucial that it's an open set. This point transforms differently from all other points, and it has serious implications in the dynamics itself. And this is the only time, I'm afraid to say this is the only time it really happens, but this is the only case I know where there is an analytic conjugacy that says that this map, remember we discussed changes of coordinates which are nonlinear, and we said that G was, I changed the coordinates, I apply my original map, this one, and I go back to these coordinates, h minus 1. And this is the only place where I know the analytic version of this mapping, conjugacy mapping, that changes this map into that map. And it's something totally easy, trivial, and it took a great mathematician to do it, but once you have it, it's very simple. So, topologically, you might have special cases, and they're very important, like this one, which you have to treat differently. So critical point is different from anybody else because it's a zero derivative, and everybody else is either monotonely up or monotonely flip. And we are allowed to do the following thing. We are allowed to make this an interval. We're allowed to have a map that says everybody in this interval gets same value, and then I go on. So now why this is a cool thing? It's cool for the following reason. The 10th map is a nice example of symbolic dynamics which is unrestricted, has no rules. For 10th map, everything is possible, meaning that if I start at some point here, it will take some value, which will be twice this interval. Then to find the next iteration, I will flip and use this point here as a starting point. So this is xn, this is xn plus 1. And evaluate that. Then I'll flip this, evaluate that. And I will make a visitation sequence of the left and right interval. So depending on what my initial xn point was, I can visit intervals. And what's wonderful about the 10th map, that I can specify every trajectory, so itinerary of every trajectory, which is the sequence forward in time, S1, S2, S3, of symbols, where symbols, we find it convenient. We could call it left and right, but it turns out there's a very simple computational reason why you give them numerical values, because we can actually do computations. And the 10th map has a property that all sequences are admissible. Nothing is forbidden. No grammar rules. So the sequences are not binary numbers. And I'm sorry, I think it's more convenient to write the sequence this way. This is where I am now. At next instant, I'll be either left or right, 2 time steps, 3 time steps, etc. So if I write this in terms of 0, 1, it looks like a binary number. It turns out, it's not a binary number, it's very closely related to binary number. So this we will use to define all possible sequences. And why are all sequences admissible? Because if you take any one interval, for example, left one, in one iteration it stretches over both intervals. So if I'm here, I can land either left and right. Same thing here. If I start on the right, I can land left and right. Now I repeat this. So no matter what little neighborhood I am, I'll eventually end up every place. So this is a beautiful example of ergodic sequences that every normal numbers goes through all possible numbers, and there is no law that tells you must not do this. You can go left and right, 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 left, right, whatever you want to do. So that's unrestricted grammar. But when you look at Rosler's system or any system that we really look at, this is extremely non-generic behavior, because this behavior requires that this return maps the place where the turning happens exactly lands at a fixed point. And it's only this trajectory that will do it, this guy. Now, if you never get as far as going the whole length of the interval in the map, so we have a gap here, then what happens is that when I look where this iterates, it ends up here, and then it does whatever it does. So it turns out that if the stretching is not sufficient, then I will never come back close to the fixed point again. And this is actually what we observe in Rosler's system. There is a fixed point here, but flow never revisits it. I can start close to it, but I'll never come back. So this is an unstable, isolated point. So it throws out all its neighbors. It's kind of me generation, doesn't like anybody. And they don't come back. They go, but they stay away. And that's very typical behavior. So generic behavior when you have an equilibrium, which is unstable, is that it's easy to find, but you don't find it in dynamics because dynamics doesn't revisit it. So this is a very special case. The generic case, there are two generic cases. You could have a map which is bigger than unit interval. So what that map does is if you end up someplace here, you actually get out of the unit interval and you're gone to come back. So that's what happened with billiards. If I didn't hit one of the two billiards, I went through the hole and that's it, gone. So that happens in that case. We talk about not attractors but repellers. Dynamics is such that almost everybody runs away except the fractal set of things that hang around. But if the map doesn't reach the unit interval, we do have a strange attractor, but it's a non-trivial grammar. Now, for unimodal maps, this is a solved problem, so that's why I'm doing it. It's the only case where we know how to specify the grammar and specify all admissible sequences. And the way we do this is we go from here to there. So what does that mean? We find a point on this map. This critical point goes around and does something. And the behavior of that, Thurston, a very wonderful inventive mathematician who is exactly my age but dead already, and has a very wonderful son that I'm friends with. But Thurston, who is a great topologist, he used this to learn about how dynamics creates topological structures, and his picture was that the way it does is the stretching and folding is like kneading. You take dough and you stretch it and you fold it and you stretch it again, you fold it. So that's kneading. And he named the future of this one point the kneading invariant. So kneading, because when you look at this one particular sequence, what you see is, you see a well-defined, totally precise sequence of symbols, you know where it goes. Tuk, 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 tuk. And kneading means is the kneading does that this point either lands on left, right, right, left. So this is well defined. Once I have this map, I can find it, and then I'll show you that I can find exactly the same cutoff point of the dike here that will have the same kneading invariant. So invariant means that topologically the infinitely many stretch and fold systems on a unit interval, all of them which have the same symbolic sequence. So that's an invariant sequence specifying dynamics of a large class of maps of this type. And so what do we learn from having a kneading invariant? So let's think a little bit in more detail. How is this sequence that looks like a binary number, 0, 1, you know, how is this related to actual temporal position in a space? So for example, if I give you a binary value of the initial point, can you read off its future? Turns out in this case you can do it. So there is a very simple, beautiful relation between these, and it's kind of easy to understand if you think about the intervals. So here is how you can think about it. So here is the interval of all points that in one step in time goes 0, called 0. You know, in first step, they're on the left. Here is the interval of all ones which in first steps on the right. So 0, 1. Now halfway down this interval, there is a dividing line which says that if I'm in this interval, one iteration later I'll still be on the left. Because, so there is an interval which we can call 0, 1, no 0, 0, in which I start and I stay in the neighborhood. So obviously it's true for neighbors at close point, but it's a whole interval, let's decide. And because this all multiplies by 2, this is all in powers of 2. So this is 1/4 of the unit interval. However, if I start here, I'll get very high up, and in one iteration I'll be on this side. So that I call 0, 1. Now here I also have 2 intervals. And here maybe it's helpful to think of a fixed point. There is a fixed point here. So if I'm in the neighborhood of fixed point, I'll stay in the neighborhood of fixed point, just get flipped. So there will be interval here, which is 1, 1. But if I'm on this interval in one iteration, you know, I get very close to the origin. So I get 0, 1, 0. So what you notice about it, this looks like binary numbers. You know, everybody here has first 2 binary digits 0, but this guy has the second binary digit not being 0. But this is weird because the binary numbers, this should be now called 1, 0, 1, 1. So what's happened is because this map is flipping stuff around, it's twisting the order. So they're obviously 1 to 1, but they're twisted. So now there is a law in our mathematics that says combinatorics cannot be explained. So this is a theorem. It's due to Feldman at Hooft in the diagram. So now you won't understand what I'm doing, but you know, sit in a room and just do it, and then you'll understand it, because watching somebody else do this is never working. So now we repeat this sequence, and we say, aha, there is a little neighborhood where for 3 steps I'm here. But on this part, for 2 steps, I'm here, and then I end up on the right side. So this guy is called 0, 0, 1. Then this neighborhood, and now you'll find it hard to believe what I draw next, but do it yourself. We'll have a property that I'll first go left, right, and left, or I'll go left, right, and right. And all it is it's just a little image of this interval. So this has a fractal structure. It's repeating itself, right? And the other image will be just flipped. So it will be it'll be blue, red, red, and blue. So the ordering in space has to do with your future, because this is your temporal itinerary. This is where you go, but it does it in slightly screwy way. So this is 1, 1, 0, I guess. I don't know. If I'm making an error, please correct me. 1, 1, 1. So that includes the fixed point. And then there is a 1, 0, 1. And there is 1, 0, 0. So the binary numbers were a little bit disordered, but it's very easy to write a rule. So you will just write a rule that says, given a sequence, if I write x in a binary basis, so I write it A1, A2, or whatever letters I use in the book, I don't remember, then there'll be a very simple machine, gamma, that converts x and tells me what its future is. And the easiest way to understand this, you can draw this as a tree, or the roots of a tree. So you can start on the unit interval. That you can say the unit interval can be split in 0 and 1. Then this guy looks like the original one, so it can be split this way. But this one is flipped, so it looks like that. So whenever I have a pink thing, I have to flip. And this will look like that. So I can just read the temporal order, the spatial ordering. So I know that the sequence, which is called 1, 1, 0, 1, no, 0, 0, 1, the way I'm reading them, this guy, is to the left of the sequence which is called 1, 0, 1. And this is true for all the unimodal maps. I'm working this out on the very simple map that has binary position in the space and the binary notation for the time evolution. Here the interval will be different sizes because this is a nonlinear map looking, But topologically, it'll be ordered the same way. So now this is a very powerful statement for us because it says that if I know several, let's say, periodic point on this map, I know I already computed something. 100,000 dimensions, I've computed 2 periodic orbits or something, and the periodic point sits someplace. Then it says that if I try to find the next one that's longer, it'll have to sits in between, it'll be ordered according to this. So we'll have a very good guess where the next periodic orbit is just from topology. And I can go from this symbolic dynamics all the way back to my flow in many dimensions and guess where the good point is that I would get for a periodic orbit. So this duality between temporal things, so there is a map which is called Bernoulli map, which is used to illustrate concepts of probability theory, the simplest model of causing toys, which is this continuous map in which in both intervals you just stretch. In that case, the binary number is also the future. But this doesn't look very physical because in physical situation we can't slice the space. You kind of stretch and fold it. So typical physical situation looks like this. But and it's a very simple relation. You just write it. Basically, you look at the sequence and you see that you have to flip the next binary number. Choose 0 and 1 depending what the preceding one was. 0, 1 it has a different rule if it's blue and pink. Totally trivial. So that's number one. In a Ulam case, with no restrictions, we can explain how everybody is ordered in space if you know what it does in time, or vice versa. If I know where I'm in space, I know the future of that point for the as many returns upon correction as many binary digits are specified. Every step in future I lose one digit because I keep stretching. So, but then there is much more, and that's the beautiful thing about needing theory, which is that you can actually precisely say what's admissibility. So grammar, I can actually describe grammar for any map, what I allow admissible sequences. Itineraries. And this is extremely important for us because what we'll try to do is we'll try to look at ergodic sets, so all horrible chaotic things that happen, and we'll try to systematically describe it by invariant solutions, which will be periodic orbits. So we'll have shorter, longer, longer. And it's work. It's always work. It's not analytic formula, except this is the only case where you can write analytic formula. Otherwise, I think, you have to compute them. And you compute them by numerical methods, variants of Newton method or variational methods or something. And knowing first how they're ordered helps you enormously because you can make good guesses how they visit around. But knowing which ones exist and don't exist is much more important. And the topology will tell us what not to look for. And the idea is extremely simple. If I have, for example, the two period 3 orbits, and I'm sure I'm going to screw them up. So there's an orbit that looks like that. So there's an orbit. I start here at x 0, 0, 1. I end up at x 0, 1, 0. So I'm still on the left side. And next iteration, I'm at x 1, 0, 0. So I'm on the right side. But in my future, there are 2 hops on the left side. So periodic orbit goes cyclically through itinerary. But there's another orbit, which, and I'm sure I'm going to screw this one up, but there's another orbit that hits twice because everything is allowed, right? Hits this way. So it does something like that. Now that orbit starts on left. So that one is x1, x0. But it'll be on the right side twice in the future. So it'll land on x1, 0, 1. And then it'll land here, x and then it will end up going on the left side. So they have different symbolic sequences, and they have very different qualitative behavior, because one of them stretches 2 times and flips once. So when you compute its stability, it'll be negative stability, because this gives you a negative slope derivative. The other one stretches once and flips twice, so you'll have positive stability. So topologically, they're totally different orbits. And they have the itineraries, but now we have a theory that says where these points are relative to each other. And because of this distribution, we find out that this point is higher than that one. So, you know, if you can understand these pictures, I'll be very impressed. But do them yourself later on. Now, suppose that we decide that our dike stops here. I put it right here. So I make map like that. What do I learn? This orbit doesn't exist. Inadmissible. Because this orbit is on part of the map that doesn't exist. There is no such orbit. So that's an example how the pruning rule comes. Your map doesn't get far enough to the end of the thing, and it cuts off all periodic points which are too high. So they're all inadmissible. And what's the criterion of inadmissibility? This point here has unique image, and everybody who strays out, so all ergodic trajectories and all periodic orbits, and anybody who has a point or any number of points in this interval is gone. It's inadmissible. But we know precisely this point in space because we know the needing invariant, we know the future of this thing, and we know how to convert needing invariant to distance in a space. So we can convert the geometry of the map in a state space, saying it doesn't stretch far enough. We can convert it to the precise point in this, you know, the symbolic dynamics representation, which only keeps care of lefts and rights and nothing else. We can find precise point there, and we know from then on that in my list of periodic orbits, everyone who has a point that sits in here is inadmissible. That's trivial to check, because how do you check it? So if we do it for, so all periodic orbits, in this case, I can just list them. There is a fixed point. There is a fixed point there on the right. Then there is an orbit that goes from 0, 1, which consists of 2 points, x, 1, 0, x, 0, 1. Then there are 2, 3 orbits. I just drew them for you. They consist in real space, you know, my state space, nonlinear, etc. Consists of 1, 0, 0, any way you want to write it, but it's just a cyclic permutation of 3. And there is another orbit. So orbit is a set of points visited in time. For periodic orbit, there are only 3 of them. So it's 0, 1, 1. Then you say, okay, in the fourth case, I have orbit like this. Well, that's wrong because I already took care of repeats of 0. Okay. So you start writing the fourth one. So there is 0, 0, 1. There is 0, 1, 0. You already took care of cyclic permutation, so somebody like that. Then there is a 0, 1, 0, 1. But that's a repeat of the 2 cycle, so that's not in the list. And it's 0, 1, 1, 1. So there are 3 orbits of length 4, and each one of them consists of 4 points. So you have this list. Now, only thing you'll need is symbolic dynamics to check whether an orbit is admissible or not. Because I have this, but I also have a needing invariant. Which is one infinite sequence generically. So it's something 0, 1, 1, 0, 1, 1, 1, 0, 1, 0, 0, 0, whatever it is, whatever the needing sequence is. And that's temporal. So this is the symbolic dynamics, symbolic string in time. Associated with it is a point in space, a binary number, which is the last admissible orbit, which is the needing orbit. Everybody to the right is forgotten. And now what you do is you go through your list, just symbol sequences, not the real physical stuff, and you cross out everybody who has a point in this list that lands in this interval. So once you have symbolic dynamics, it's extremely powerful. It's topological, but it tells you what's possible and what's not possible without doing calculation. The only calculation you have to do is you just have to precisely follow the needing invariant. So your symbolic dynamics is as precise this trajectory is. And because the system is unstable, typically you can do it only for finite time. But because system is exponentially unstable, these intervals get very small. So finite time is usually good enough because, if I get this just, here it goes by powers of 2 and here it's non-uniform, but they're very small intervals. Because to have a precise future for unstable system, you have very narrow initial values which you follow it for and exponentially small. So this is now the great thing. If you can get a grip on topology, so don't go fishing, stay at home and think. If you can get grip on topology, you'll be able to make a catalog of all possible solutions before doing anything else. Just by thinking before actually computing. And computing can be very expensive because some of these problems are quite difficult. Not the one-dimensional maps, but things that have to do with dynamics, field theory, things that have many degrees of freedom. Now you say, well, okay. You cooked up, the Slayer cooked up some map, and that map it's so contracting that in its return map, I have essentially one-dimensional dynamics. But this is not true in usual. For example, if I have a Hamiltonian system, it's not very contracting and it preserves areas in phase space. There is alluvial. So what am I going to do then? I take something, so I take a piece of dough. This model was I take a piece of dough, I fold it and press it, so it gets thinner. I fold it and press it. And by the time I've done this 10, 11 times, it's few Fermis thick. But real dough is volume preserving, so it won't work. For example, we care about Hamiltonian mechanics, but this possibly cannot work there. It does. And I already did it for you once because I showed you in this virtual lecture, which I hope you will, at least 2/3 of it have sound on it. I showed you that for billiards, we can do the following thing. And the billiard is a perfectly Hamiltonian system. So real physicists, and it turns out actually the engineers are much better than we are. How is that spelled? Do mechanics. but they don't call it this. They do, Hamiltonian dynamics. So for real physicists, world is perfect, energy is preserved, there is no dissipation. That's only for chemists and stuff, the real physics. Now, people who do robotics actually know how to do this much better than physicists, but that's just a side remark. So this possibly cannot work because there will be no one-dimensional map that'll do this. If you do it for a 3-disk system, just as a teaching exercise, I told you 2 things, apparently both of them unmotivated. I told you, don't look at a pinball just bouncing around. Look at it in Poincaré section. The way it's moving here is not very important. It's important what it hits and where it goes, and that's captured by Poincaré section. So in Poincaré section, so on. And the 2 apparently is not making any impact whatsoever. And quotient the symmetry. So look at the phase space M over G, which is M over group of 6 elements called C3V, or called dihedral group of 3 elements at the end. And all that means is that I really should not look at this whole world the way it's done here. I should just look at what happens here with the mirrors. So this is quotiented space, M divided by symmetries of the thing. Now, you don't have to listen to me, and you don't. So if you do this for the whole system, there should be 3 Poincaré sections. There should be some complicated scheme of going from this Poincaré. But if you, do the smart thing, which our forefathers, this one they've invented, Kronecker probably invented it in 19th century, 1880s or something. In quotiented space, what happens is, as I go here, I look out. So there is one of my coordinates is where am I on the disk? That's S. And the other coordinate is what is my parallel momentum? P, which goes from -1 to 1, because we decided mass is 1 and velocity is 1. And that just means what is the angle that I'm going out. I find out that there is, for every point here, there is a bunch of angles that all hit the next one, and another bunch of angles disjoint that hit the next disk. Or if I fix the angles, there is a bunch of intervals that go and hit this. So there will be strips, and these strips are easy to draw. So in my lecture I screwed them up, but here what the strips look like. And there is a strip here in which I go and come back, which in big space corresponds to bouncing to the next disk and coming back. And there's another strip here which I bounce through this mirror and come back, which in big space means that I go around the disk. So I come from disk and go to the next disk. So that's the topological distinction between these 2 strips. And when you look at it, they really look like these things. One of them has flipping, one of them doesn't have flipping, because there's an extra mirror here. So that's what happens forward in time. Now backward in time for dynamical systems like billiards is very easy, because backward in time means I just reverse the velocity. So time reversal is very simple. But that means that this strip of initial conditions, let's call them 0 and 1, in the future, there is also a strip of initial conditions which is just flip of this picture. So that looks like that. And this guy also does the same thing. So it's just a mirror image. Past is just the mirror image of the future for Hamiltonian system. And system is Hamiltonian. So this is a Liouville volume. This area is preserved. So if I start with an area, in an iteration it will remain the area, but it's partitioned now in a way that there are strips in which I stay in a system one bounce forward because I start and I still bounce. And there's a complement in which I start and I get out. So the rest of the space outside of these strips is not there. So we can take a Hamiltonian system, and by looking at future and the past, we can, for example, divide it into 4 regions, this different future and the past. And we can figure out where the fixed points are. So 0 fixed point has to be in here. It'll be this guy here going tuk, 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 tuk. And there will be a point that goes around here. It'll end up in here. So we can find fixed points very easily. We can find periodic points very easily. And now, what is the equivalent of the Dike map? It's actually, you can think of it as 2 Dike maps, one in the past, one in the future. That's hard for us to draw, but producing a representation of this is very easy. So this is like now making a map of Manhattan, where we just take care of the blocks, but we put them together, we ignore the avenues. So we slice them together. So what we can do is, we can take the world in which this is 1, 0, 0, 0, 1, 0. So we use our future labeling that we already developed there. 1, 0, 1, no, 0, 1, 0, 1. And then throw away all the stuff that runs away. So this piece of past and future corresponds to a 0, 0 part of this. This piece corresponds to 1.1 and 0.1, 1.0. So what it means is, even though this is not a one-dimensional problem, we can get very good symbolic dynamics of it anyhow, just by carefully looking in future and past, because if something is unstable in a Hamiltonian system, it means one eigenvalue contracts and one expands because the volume has to be the same. So going past in the future, you're finding out instability along the one direction, and looking in your past reverses what's expanding, what's contracting. So you're looking at instability in the other direction, and in the limit, every point in this graph, so if you give me a binary sequence, I will always be able to design here a region which is of this, 2 to the n's, if it's n steps, small because I'm partitioning by halves. I'll always be able to go back to the physical system because I know how to map them. And I'll always be able to find corresponding trajectory periodic orbit. I can see a great deal of suffering. Maybe you should sometimes ask questions. I mean, it's not strictly forbidden.
So the blue lines are past?
In this case, blue lines are past and pink is future.
And what did you make on the right-hand side?
There's a bright gay future ahead of it. On the right-hand side, what I do is, in the physical space, the intersection of the past and the future are some kind of rectangles, which are laid out in weird ways because it's a physical space. So they're rectangles and they actually have curved borders because there's actually stable and unstable manifolds, these things, which I'll explain in a second. So in the physical space, dynamics is partitioning the physical space. And it says if I think carefully, so what I'm doing in this case, these two edges are actually the edges of the disks. So that's equivalent of what we did with a critical point, the needing invariant. We look at the last orbit that's possible, and we trace it out. But because it's a two-dimensional problem, that last orbit sits on a line. Because, as I change my position, the angle changes. Where is the last one? So every point here has a different last one. Points. That's how you get these curves. The pink one's forward in time. Now you ask yourself, where did I come from? And again, your freedom of where you came from is bounded by these two edges. So if you were not within this interval, you're not one of us. You came from outside. We don't want foreigners. So this is people who only sit inside for all times, back and forward. So this is a repelling set, but it's very intuitive about how you get symbolic dynamics. It says, look at all these strips. Now, once you have these strips, it looks like Atlanta. All the roads are going, God knows where, they're all at weird angles, but you just straighten them out. So you get a map, like, subway map of Paris or London, Looks nothing like the map of the actual system, geographical map, but is what you need. You need topological information to get from here to here, and this rectified map keeps it. And the way we obtained the rectified map is we said, well, we don't care about anybody who is not one of us, so doesn't stay with us or came from someplace else. That's why we call a repeller, repel everybody except us. So the only important part of dynamics is contained in these four boxes, because these are things that at least for one step in time, back and forward, are still part of the game. And then I make them fat, I turn them a little bit around. I forget what's in between. So again, blocks, I just forget the street. I just put the houses adjoined. So this line represents the whole interval of things that ran away. And I get a very nice topological map. It's a generalization of this thing. It's called Baker's map. It's generalization of one-dimensional thinking in two dimensions.
So these are the trajectories that will never escape the balls?
No, these are trajectories that won't escape for one time forward, and they were with us one time backward. Now if I look 2 steps in forward, most of them run away. Because 2 steps forward in time, they always have the same choices. They either hit one of the disks or run away. But running away is pretty big, because in this case the disks are separated. So then what will happen is that I will have to magnify this picture. So if I look at this region here, magnified, physically what will happen is this region looks like that, but actually within it, forward in time, there'll be 2 little strips of things that survive. And backward in time, there'll be 2 little strips of things that survive. So each one of them will be 8 little regions of things which are with us twice in future, twice in time. So they will look like that. There'll be, 4 regions within each one, which means that here, I just subdivide everybody here into four regions, and I give them names. So this one is, 1, 0, 0, 0. This is 1, 0, 1, 1, according to the rule we already learned. So even though the physical set is getting thinner and thinner, I can have a nice map in which I take care of everybody. And once you understand this, and once you understand the needing theory, yes?
So where are these odd number periodic always
Yeah, you know, I could decide to just split it 2 times forward in time and once backward. Then that would look like that. I'll have 3 digits. I just draw it an intersection of future and past because it's prettiest this way. And, you know, you get the nicest fractal. Otherwise, what happens is they get thin in one direction and long, and you know, long in the other directions, so they look uglier. But they're all equivalent because if I know 3 steps of future, I can just move 1 step forward, and then I have no 1 step of past and 2 steps of future. So they're all equivalent, they're just maps of each other. But if you do it in this way, that you go the same amount of time forward and back, it's natural for Hamiltonian systems because they're reversible, and but you know, then you get very pretty fractal sets to discuss.
Do all Hamiltonian systems look like this, or only this one in particular?
This is chosen. So this is harmonic oscillator of chaosbook.org. This is chosen to explain all concepts of symbolic dynamics in such a simple way that anybody can understand them. The Hamiltonian systems are almost never like that. So this actually works in the following situation. Suppose you have a plane with 3 electrons stuck someplace, but even that's a little bit worrisome. But 3 repelling things. You have a potential which has 3 peaks, and you shoot something through which doesn't have the energy to be above the peak. Then it'll bounce around, and topologically it'll have the same property. It can, and if they're repelling,
it's fundamentally about the topological sort of properties of the space.
Yeah. So basically, if you have a topology, they have 3 regions that are repelling. Then this will be the class of maps that are like a 3-disc billiard, or it could be 4 regions because you have graphene, you have some crystal, or hexa, but you'll have this dynamics classically. Now, when you have bound systems, things get harder, and in this one-dimensional system, we have the theory that says even the system bound, if I know the needing invariant, this is beautiful, I know everything. Now, for these guys, it's more difficult. So I've developed a theory called theory of pruning fronts, which is supposed to do it for these things. And part of it's now officially mathematics, so I cannot read the papers anymore. They're totally amazing. And what I like about mathematicians is, because I'm lazy, I design examples by hand. So I drew some pictures, and my mathematician friend, who is brilliant and now in Rio de Janeiro, he shows that every example that I drew by hand cannot be realized by dynamics. So all my examples violate, because he has a real theory of pruning fronts. But anyway, so there is some beginning, but that's an open problem. So there is a class of problems that look like generalization of unimodal maps. Unimodal maps are things that are repulsive on intervals. And in some Hamiltonian systems, you can think of things which are repelling. Is this real time?
Yes.
Yeah.
Really? Wow. The time has dilated for me. I'm on a graduate student schedule. Go to bed 4:30, get up at 8. So the time is weird. The concept of time is eluding me right now. So what happens is, if you have repelling things, you can find sets of analogs, and they work, for example, in celestial mechanics. So if you're interested in what asteroids will run away and stay, this kind of ideas work. The topology is very important for that. And again, it has its roots in work of Poincaré, Birkhoff, etc., because they had needed. And Burak is also in a different time zone. So now, if they're attractive, then you have to think again, because you can bounce off, but you can go around. So you'll have more symbols, because you'll have to count possibility that when they came back, or you went around and came back. Yeah, so you'll have to work it every time.
It's even for Hamiltonian systems because you have past and future are equal on equal footing, right?
Well, the interesting thing is the time is always one-dimensional, but the space partitions get more and more dimensional because the space partitions, in a way that maybe I'll start explaining, the way they're really done is that you look at unstable manifolds, and these things are defined in many dimensions. So unstable manifolds can be high dimensional, and it's this thing that actually produces the partition. The invariant properties of dynamics, everybody will get the same unstable manifold, they'll get the same topology. So this thing, in any representation of the system, will have same topological properties. Let me, so it's confusing because time always tells you 0, 1, 1, 1, 0, but it actually is going to connect more regions. I showed you it works in one dimension, which is okay, one-dimensional thing. Now I showed you it works in 2 dimensions. Now I cheated in the following way. In the 1 dimension, I showed that it maps on the forward sequence. I only care about forward sequence. In 2 dimensions, I needed a bi-infinite sequence. I needed to know where I came from, where I'm going to describe the plane. So it's not clear how it's going to work in higher dimensions. So I'll leave it as an open problem for it. But it works at least in these cases. And we use this in very high dimensions. So students that work like Norman, that work with Professor User, I do this in 5 and 10 degree of freedom Hamiltonian systems. But they will need to do something like that. So to explain that what this is really, you don't see it very clearly because you don't know what unstable manifolds are right here. I have to explain, globalization, going global. And I never understand why people are Luddite and so much against globalization, because it's a scary thing, but it's a wonderful thing. And I'll try to show you that it's scary and wonderful in dynamics, where it's easy to discuss. So when I have, easiest thing to do is to do it first for the equilibrium. So you have a flow. We learned how to explore its near neighborhood by learning about linear stability. So we learned that every equilibrium has a set of d eigenvectors, and some of them are expanding directions, and some of them are contracting. So let's say this is expanding, this is contracting, expanding, contracting. So linear as neighborhood, there was a natural coordinate system for linear as neighborhood. It is not your coordinates of this room. It's not orthogonal, because dynamics doesn't do that, because the Jacobians are not symmetric or self-adjoint matrices. So it's eigenvectors, do something. They're linearly independent, but they're eigenvectors, so they're natural coordinates for the problem. So it told you, this is how I look at my neighborhood. I find the orbit, I look at its linear stability, and then I can look at the eigenvectors, and as long as linear approximation is pretty good, this is a good map of my neighborhood. So even though I'm on a round Earth, the flat map in this room is good enough to do this room with very high accuracy. So that's the idea of linearization locally. But we don't actually care about local things, because we would like to understand what happens every place. What's global. By the way, I put this in. What stays in the box, which is over there, Society of Physics students, this is the box. So, whatever bounces in that room here stays there forever, and doesn't go to Las Vegas or any place. So this is the box. Just in case. So how do we go global? There's an invariant way of going global. See, there are preferred directions here. So what I can do is I can take some number of little points here where linearization is good, and I can run them through my dynamical system. Now what the dynamical system says, they'll be moving along this line in the beginning, but then nonlinearity is kicked in. And what will happen to them is that they will start marching on something that eventually has to curve, because we're in a system where we have recurrences. So even though we can go far away, we are forced to come back. And we saw this in Rosler map. That's exactly what that return map was built in. It was following this. But I can do this in any number of dimensions. And of course it gets harder. And the stable manifold, I have to look at my past. So they're the things that came from someplace and did something. Locally they're linear, but way back in the past they were very far away. You know, they were marching toward me and they're doing a complicated motion. But this is a very special motion. It's like one of these edges here. This is an invariant motion because this is associated with an invariant solution with its invariant stability vectors, with its invariant multipliers, stability multipliers or exponents. So this is built into the dynamics. This is not external. So if you change your coordinates, this will change shape. But any intersection here, for example, will be intersection because it's topological property of the flow. So another good person, I guess I'll do it briefly next time, Marcel Henon. So this is a brilliant astronomer, a French style, so he knows his mathematics, just like Lorentz was a brilliant meteorologist because he was a student of Birkhoff. Marcel Henon, who is currently dead but was alive until 6 months ago or so, Marcel Henon said, well, you know, I don't understand Lorentz attractor, just like Rosler. Let me just produce a map that mimics what Lorentz attractor does. So he produced something called a Henon map. And the way it was done in 2 steps. Yves Pommeau, who is a great statistical mechanics guru in Paris, France. This is in Nice, by Mediterranean. He ran Lorentz on a computer. He tried to explain to Henon what it does. And Henon wrote a map where all these things that tell you about stable and unstable manifolds is very explicit. So please read the book and I'll briefly either video that part of the lecture or do it next time. And you're lucky, maybe today we have the problem set from the next week. I'll see where we do have it. So you get a pass for a whole week of no suffering.